All right, we are now in a much noisier lab. We're going to continue with more of our chapter, whatever this is, 17 lecture. We left off, we just started talking about strong bases. In the previous lecture, we went through all of the fun with ice tables that we can have with weak acids. And so we're picking up with weak bases. A weak base is analogous to a weak acid. A lot of our weak bases produce OH minus by accepting a proton. This makes them a Bronsted-Lowry base. They accept that proton from water. In our generic equation, B is base, our weak base. BH plus, it's accepted that proton from the water and it has produced hydroxide, sort of indirectly. So it's not an Arrhenius base, but it is a Bronsted-Lowry base. Ammonia is an example of a weak base. It can accept one of these hydrogens from water and become ammonium, thereby producing hydroxide in the water solution, the aqueous solution. Similar to how we have Ka, we also have a Kb, our base ionization constant. This quantifies the strength of a weak base. We use our equilibrium equation for our base in solution. We put products over reactants. Just like with all of our other equilibrium constants, and we get our Kb expression. Notice that we're omitting H2O because it's a liquid. So solids and liquids, we don't want them. We don't care about them. A smaller Kb, more negative exponent, means a weaker base. Another thing that we can do with K values, like our Kb, is we can add a little p in front and calculate something called a pKb. The p, of course, being negative log. So negative log of the base ionization constant gives us the pKb. We can do a similar thing for acids, weak acids. I don't know why it wasn't in the slides, but pKa is negative log of Ka. Some of our common weak bases are things like the carbonate ion, methylamine, ethylamine, the methyl, the ethyl, with nitrogen and some hydrogens making it an amine, ammonia, and so on and so on. One common theme is that we've got a lot of amines, things with nitrogens in them. So that's a common theme among our weak bases. Not all of our weak bases are going to be amines. But this gives us a means of identifying some of our weak bases. As mentioned, a lot of these are amines. We can think of those as ammonia, NH3, with hydrocarbon or multiple hydrocarbons substituted for a hydrogen or multiple hydrogens. And the reason that these act as weak bases is that they've got lone pairs. And lone pairs are like little lassos that they can throw out and catch hydrogen off of a water molecule and temporarily requisition that water molecule's hydrogen for its own use. So we've got ammonia up top. It can become ammonium. We've got methylamine because it's got one carbon attached to it. That would make it a methyl group, like methane. And that can form a conjugate acid. Just like with our weak acids and our strong acids, we can find concentrations. So with our strong bases, the autoionization of water is negligible. So most of the time it'll be negligible. And finding the hydroxide and pH of a weak base is similar to finding the hydronium concentration and pH of a weak acid. So it's similar steps as with weak acids. We do have to add a step or two, depending on how you solve it. Since we're going to be finding the hydroxide concentration, if we want to find pH, we'll have to convert to hydronium, or we'll calculate the pOH and then find the pH from that, using that circle of pH from the first lecture in this chapter. All right, let's find the hydroxide concentration and pH of a strong base solution first. There's two clues that this is a strong base solution. What's one of them? It has hydroxide. That's a sign that it's a strong base. It's also ionic. That's an important factor. The other clue that it's a strong base solution is because the title of the slide says it's a strong base solution. So if we want to find our hydroxide concentration, we can write a dissociation equation for barium hydroxide. It's going to produce barium ions, and we're also going to produce two, because of the subscript, two hydroxides per barium hydroxide. So starting from our 0.010 molar barium hydroxide, we can use our dissociation equation and some stoichiometry from that to calculate our hydroxide concentration. So we'll have 0.02 molar hydroxide, double the concentration. If you feel comfortable just using the 2 subscript on the hydroxide and multiplying by 2 because you see that there, that's fine with me. You don't have to show me the dissociation. You don't have to even necessarily write out the calculation, just write out that you're multiplying by 2. Units would be great, but I'll understand what you're doing. Okay, so we found our hydroxide concentration, and now we have to find our pH. Since our circle of pH is a circle, you can get to any of the points by going either direction around the circle. I don't remember which directions I made on the circle. I'm going to choose to solve this by going through pOH. Let's make those parentheses. So the negative log of 0.02, our pOH 1.69 and change, and pH plus POH equals 14. So 14 minus 1.69 dot 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 equals pH. So our pH here is 12.3 and some change, but we'll just call it 12. Questions? Great. We can also do stuff with weak bases. So let's find the hydroxide concentration and the pH of this methylamine solution. Methylamine's a weak base. Part of the reason that we know that it's a weak base, we're given a Kb value and it's not 1 or 2 or whatever it would be. Weak base. So we are going to do an ice table. So we've got our weak base. That's going to go on to produce Hb plus and OH minus. And we write in our initial change and equilibrium. Our initial concentration of our weak base is 0.33 molar, and we initially have none of our Hb plus, and we've got a negligible amount of hydroxide. Our equilibrium, I'll include the water. Our equilibrium is going to look something like this: Hb plus and OH minus. Keeping in mind that water is a liquid, it won't show up in our Kb expression. Since we initially have 0, absolutely 0 of our Hb plus, this reaction can only proceed in the left to right direction. So it can only proceed in the forward direction because we don't have any of one of our products. So we can't move in the opposite direction. So our change values are not plus x, but minus x for our base. And we're going to be producing some of our conjugate acid and hydroxide. So our equilibrium values, 0.33 minus x, x, and x, respectively. We then write our Kb expression, concentration of the conjugate acid times the concentration of the hydroxide over the concentration of the base. And we can substitute in some of our equilibrium, all of our equilibrium values. Let's go ahead and try our X's small approximation. So if we try our X's small approximation, that gets rid of the minus X in the denominator. And we'll end up with 0.33 times our KB value, 4.4 times 10 to the minus 4, and that's equal to X squared. To undo the squared, we'll do the square root of both sides. So in this case, X is equal to 0.01204 dot dot dot. Call it molar if we want to. Checking our X's small approximation, we get about 3.7%. So our X's small approximation works here. So this X value is the same as our wrong thing, our hydroxide concentration. It's also equal to our HB plus concentration, but we don't really care about that, at least for this question. So our hydroxide concentration, 0.01204 dot 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 molar. Which gives us a pH of 12.08, so basically 12. Questions about any of that? All right, since weak bases are so similar to weak acids, we don't do a ton of weak base examples. And I know you're thinking to yourself, you know, this has been kind of rough, but I bet it could get harder. How could we make it more difficult? And I'm glad you were thinking that, because I've got the answer for you. So we've got ions and salts. Some ions can act as bases because they're the conjugate bases of weak acids. So this is where conjugate acids and conjugate bases finally starts to become a little bit useful. It kind of, I don't know, for me at least, feels kind of hollow talking about it in 3A. So we've got conjugate bases of weak acids, so we have to be able to identify weak acids so that we can identify what their conjugate bases are. So like HCO3 minus is an example of a conjugate base of the weak acid carbonic acid. Ions must be paired with a counter ion to form a salt, that is an ionic compound. So you might see it as sodium hydrogen carbonate, baking soda. And then in solution, we have the conjugate base of the weak acid. So if you add sodium bicarbonate to some water, it's going to slightly raise the pH since we have that conjugate base. We can think of any ion as the conjugate base of an acid, as long as we can come up with an acid, of course, that goes along with that anion. Generally, A minus is going to be our conjugate base of the acid HA. So possibly with an equilibrium arrow, we've got H plus and A minus. HA being our acid, A minus being our conjugate base. And that's all fun and good. But not every anion is going to act like a base. It depends on the strength of the acid. The conjugate base of a weak acid is a weak base. The conjugate base of a strong acid is pH neutral. The reason for this is for the weak acid, we have an equilibrium expression. Some of our conjugate base is going to go back to form the acid. It's going to react with H plus and go back to form the acid. If we have a strong acid, it's only going in one direction. So for our strong acids, conjugate base, we get no reverse reaction occurring. It completely dissociates. We're not going to have any of the HA left in solution. It's not going to reform. It's only going in the forward direction. And I'm going to rewrite out one of those points so it's a little easier to find. The conjugate base of a weak acid is a weak base. Again, that's because we've got the double-headed arrow, we've got an equilibrium process. We can go in both directions, not just one direction. Some examples of this. The chloride anion is pH neutral because hydrochloric acid is a strong acid. The fluoride anion is basic. It's a weak base because hydrofluoric acid is a weak acid. It's a weak acid, so our reaction can go in both directions. That's one way of thinking of it. The other is our fluoride ion has a strong affinity for protons in solution. It's going to pick them up. And here's a table of a bunch of acids and their conjugate bases. So on the left side, we've got a bunch of acids. We've got some strong acids like HCl, HBr, and HI would also be in there. We've got nitric acid, the first proton on sulfuric acid. We've got a bunch of weak acids, things that we should know, like the second ionization of sulfuric acid, so HSO4 minus. We've got hydrofluoric acid. We've got acetic acid and other things like that. Since these are all weak acids, their conjugate bases are going to be weak bases. classify each of these anions as a weak base or pH neutral. So what we want to be thinking about for this type of problem is if we add hydrogens onto that anion, is it a strong or a weak base? So if we add a hydrogen onto our first one, we get HCHO2. If we add a proton to ClO4 minus, we would get HClO4. And then you'd have to identify, is it a strong or weak acid? Any guesses or knowledge about whether perchloric acid, our second option here, HClO4, is a strong or weak acid? Perchloric acid is a strong acid. This was one of the ones on, I think it was 6. There were 6 strong acids that you were supposed to memorize. This is one of them. So perchloric acid is a strong acid. So when it dissociates, it forms H+, ClO4-, and it only goes in one direction. So ClO4- is pH neutral. You don't necessarily have to go through all those steps to get to the correct answer, just trying to show you some of the things you might think about to arrive at that answer. Any guesses about HCHO2? CHO2- is a weak base. HCHO2 is a weak acid. One of the ways that you might identify that it's a weak acid is knowing what it is and just knowing that it's a weak acid, obviously. The other way that you might recognize it is it kind of looks like our vinegar friend, acetic acid. Which is HC2H3O2. It's got the CHO thing in there. An indication that it might be a carboxylic acid. Carboxylic acids are weak acids. So that might be how you'd identify it. Or you would just know it's not on our short list of strong acids, so it must be a weak acid. And since that's a weak acid, CHO2- is a weak base. So more about anions as weak bases. We can determine the pH of a solution containing an anion that acts like a weak base, but we will need to know the Kb value. If you try to look up the Kb value, there's a good chance that you'll just get people asking questions on Chegg or other places, and you'll be paywalled and you won't get to see what the Kb is. Wikipedia is probably not going to have that information readily available for you. You would be able to find a Ka value, especially in the book. So we need some sort of a relationship between Ka and Kb. So we've got on the left our acid form, and on the right our reverse. That would be our base. So acid, base. So for our acid, we can come up with a Ka equation. Concentration of H plus times the concentration of A minus over the concentration of HA. We're omitting the water because it's a liquid, so we don't include it in our equilibrium expression. For our base, Kb equals concentration of hydroxide times the concentration of HA over the concentration of A minus. And you may notice that we have in our Kb, HA over A minus, and in our Ka, A minus over HA. So if we multiply these two terms together, that would look like this. Our concentration of A minus cancels. Our concentration of HA cancels. And we're left with the concentration of H plus times the concentration of OH minus. And what is that? Equal to. It's not H2O. It's related to H2O. That's our Kw. So the relationship that we're proving here, showing here, is that Kw is equal to Ka times Kb. And this is really helpful because if we have a Ka value, we know what Kw is, at least at 25 degrees Celsius. It's 1 times 10 to the minus 14. And so we can calculate a Kb value, and that unlocks our ability to solve problems with these conjugate bases and later, possibly, conjugate acids. You don't need to know how to show this derivation. This is just proving to you this isn't just coming out of nowhere. The hat man didn't gift me with this knowledge. It is real. So let's use our newfound knowledge. We want to find the pH of a 0.250 molar nacho solution, and we're given a Ka value. An important thing to note here is that we have a Ka value. Ka values are for acids. And what I'm calling affectionately nacho here is the conjugate base of a weak acid. So the way that our conjugate base behaves is going to need a Kb. To solve this problem. There's maybe a way that you could solve it with Ka. I think it's simpler if we just calculate the Kb and do it like all of the other ice tables that we've done today. So using our new knowledge that Ka times Kb equals Kw, Kb equals Kw over Ka. So 1 times 10 to the minus 14 over 1.8 times 10 to the minus 5. Kb equals 5.5 repeating times 10 to the minus 10. And we can draw up what our Kb would look like from an equation with what we know is a weak base. Our acetate is going to react with water as a weak base. So we'll be forming acetic acid. And hydroxide. Our Kb then is concentration of acetic acid times the concentration of hydroxide over the concentration of acetate, C2H3O2, minus. And then we can use our ice table. So we've got our weak base, the acetate, C2H3O2 minus. We've got Hb plus, that's our acetic acid. I guess it would be B minus Hb. Doesn't really matter as long as you know what you're doing. And the hydroxide. Writing out our ice on the side, our initial concentration of acetate C2H3O2 minus is 0.250 molar. Our initial concentrations of Hb are 0. Our initial concentration of hydroxide is approximately 0 because the autoionization of water is really weak. All right, so drawing in our changes, we've got minus x plus x plus x. Sure looks familiar if you've been here for so far both lectures. It's the same x values. It's the same thing. We're doing the same stuff over and over again. It's not insanity though, because we're getting different outcomes, sort of. And so we make our very familiar K is equal to x squared over our concentration minus x from our ice table. Any questions? We're not done yet, of course, but questions, confusion? Very cool. We can try our x is small approximation. And so we get x squared is equal to kb times 0.250. So x is equal to square root of our kb times 0.250 plug that into our calculator. $1.1785 to the 1, 2, 3, 4, 5, negative 5 times 10 to the negative 5. That is hopefully, obviously, smaller than our 0.250 by quite a lot. Our x is small approximation works great here. And since our concentration of hydroxide is equal to x, and we just solved for x, that means this 1.1785 times 10 to the minus 5 is also our concentration of hydroxide. Then we do concentration of hydroxide to POH to pH by the same steps that we've been doing previously. So negative log of our concentration of hydroxide, 14 minus POH, and our pH, 9.07 pH units. So we've added a couple more steps. The main step that we added here compared to our things before was using this Ka times Kb equals Kw. That was kind of the main step, a very important step. Otherwise, it's the same ice table. The x is small approximation works. And then we do a little bit of rearranging, reformulating to calculate our pH. Questions? All right, checking our concepts. Which of these anions will behave as a weak base? Got some immediate answers for C. Love to hear it. Fluoride is going to act as a weak base. It's the conjugate base of a weak acid. Hydrofluoric acid. The other two are conjugate bases of strong acids so they're pH neutral. Doesn't affect our pH at all. All right, the other side of the coin, we can also have cations that behave as weak acids. This is a similar idea to anions that are weak bases. So we've got three categories of things. We've got cations that are counter ions of strong bases. These are going to be pH neutral, just like our conjugate bases of strong acids were pH neutral. So we don't have an equilibrium. The strong bases don't reform. So things like calcium, sodium, and potassium. From calcium hydroxide, sodium hydroxide, potassium hydroxide, those would be the strong bases. We know they're strong bases because they're ionic. They've got hydroxide. We also have conjugate acids of weak bases. So if we take a weak base and add a proton to its formula, that gives us BH plus, the conjugate acid of a weak base. And that can produce H3O plus and reform the weak base. This is analogous to the weak acid's conjugate base that we were talking about before. We're just switching the acid and the base. So we've got a weak base. It's going to form a conjugate acid in solution. That can also go back to reform the weak base. And we've got a third category, because I know you were thinking it, why can't we make it more difficult? Why can't we add more things to remember? I've got you, don't worry. We also have cations that are small, highly charged metals, such as, these are ones you should know, aluminum and iron 3+. These also form weakly acidic solutions. The way that this works is the ion becomes hydrated, so you add waters to it. We get aluminum, in this case with 6 waters. It's still got a 3+, and the hydrated ion can act as a Bronsted-Lowry acid. So if we have another H2O, that H2O can seal one of the H's, one of the protons, from one of those hydrates and go on to form H3O plus. So Al3 plus and Fe3 plus form weakly acidic solutions. You would see these being introduced into the solution with some negatively charged counter ions, something that makes it soluble in solution. All right, knowing what we know, classify each of these cations, positively charged ions, as a weak acid or pH neutral. So again, we're thinking about what sort of base would this have been produced from? Would it be produced from a strong base? Would it be produced from a weak base? Or is it just a small, highly charged metal? All right, what kind of base could lithium have come from? A strong base or a weak base? Strong base, it would have come from maybe lithium hydroxide, LiOH. That's a strong base. Since it came from a strong base, lithium ion is pH neutral. Or since it could have come from a strong base. The strong base means that it completely dissociates. Those don't have a very strong affinity for each other. It's going to stay dissolved as lithium ion. CH3, NH3+, would that have come from a strong base or a weak base? From a weak base. The tell here is that we've got nitrogen. Nitrogen means that it's an amine, so this would have come from methylamine in this case. Just pull off one of those H pluses. The H plus, I guess it is. And since it's from a weak base, that means this is a weak acid. And then our last one, iron 3+, would that have come from a weak base or a strong base? Probably not. This was our third category, so it's probably neither of those. It's just a small, highly charged, relatively highly charged metal. So iron 3+ is a weak acid. Questions about any of those three? Another tell for A and B here. Lithium doesn't have any hydrogens to give off. It would have to accept an OH minus in order for it to have any sort of acid potential, whereas CH3 NH3+ has some extra hydrogens possibly in there that's giving it this positive charge. It could give one of those away, and that in that way it would work as a weak acid. All right, we will wrap up after we get through these classifying salt solutions. Question?
Does it matter that it's a transition metal? Is it just iron 3+, or could it be any?
It's not just iron 3+. I would say probably any of your top row of transition metals, since we specified that it's small metals and highly charged. So if it's like a 3+ or higher, it's like chromium is also in that top row. Chromium can form hexavalent chromium 6+, so that I would expect to also be weakly acidic. And then aluminum, which isn't a transition metal, would also be included with that. So we'll say top row transition metals with 3+ or higher, also aluminum 3+. That would be like a good general concept for those small, highly charged metals. So if we have salt solutions, the pH depends on the cations and anions that are involved. If we have no weak acid and no weak base, right? If we have cations ions that don't do any of that, like if they're only from strong acids and strong bases, then it's going to be pH neutral. There's not going to have any effect because all of our ions are pH neutral. So that's one possible case. So like things like sodium chloride, the sodium from sodium hydroxide, perhaps that would be the equivalent. Sodium hydroxide is a strong base. The chloride from like HCl, HCl is a strong acid, and so the chloride then would be pH neutral. Same idea for the rest of the examples. We've got another option. We've got the cation, in this case, being the counter ion of a strong base. So cation is from a strong base, meaning that that ion is pH neutral. And the anion is the conjugate base of a weak acid. So we've got no acid contribution. So like with NaF, we've got sodium and fluoride. So that sodium may be from sodium hydroxide. That's a strong base. So sodium is pH neutral. Our other ion, though, famously from hydrofluoric acid, which is a weak acid. So F minus is a weak base. So in this situation, since we don't have an acid, because our sodium is pH neutral, but we have a weak base, this would be a basic solution. So we're just comparing the contributions of our two ions. And then we've got the other side of it, so salts in which the cation acts as an acid. This is a little bit more complicated. So our cation is acidic and anion is the conjugate base of a strong acid. The reason I say this is a little bit more complicated is because we can have things like iron 3+ and the aluminum ion, where those are small, highly charged particles, and so those act as acids. Or act to form acidic solutions. And then we've got chloride and nitrate. Those are conjugate bases of strong acids. So their contribution is null. They're not contributing anything pH-wise. They're just kind of there. And then our fourth and final scenario is if both of them contribute. So both weak acid and weak base effects. The bigger K wins. So if our Ka is bigger than our Kb, that's going to be acidic. If our Kb is bigger than our Ka, then it'll be basic. Questions? So really, all we're like these 4 scenarios, you don't have to memorize them or anything. We're just thinking about, do we have something that acts as a weak acid? Do we have something that acts as a weak base? And what sort of effect are they going to have? If we just have the weak acid, it's going to be acidic. If we just have the weak base, it's going to be basic. If we don't have either, it's going to be pH neutral. If we have both, it's just a matter of which one is stronger. And then here's a summary slide that is just kind of all of those situations baked together. And we'll stop there for today.